In this video, we're going to talk about derivatives of exponential functions. Recall that an exponential function is a function in the form a raised to the x power, where the base a is a real number. It's got to be greater than 0 and not equal to 1, and then our x is our variable. So on here, what we've done is we've defined the derivative of a general exponential, where we've allowed the exponent to be a step piece. So instead of saying x is the singular exponent, it could be actual multiple terms up in the exponent. So on here we said derivative with respect to u of a to the u equals the natural log of a. Basically there what you do is take the natural log of the base piece of your exponential. So we've got that as the first piece. Then you multiply the exponential function itself. And then you multiply the derivative of your power. So always think of this derivative as a three-step process when you actually go and perform the derivative. We have a special case for e to the x. E is an irrational value, and I've written part of that irrational value out here. And its derivative is so simple that sometimes it's just really nice and easy to remember that the derivative of e to the x is just itself. The reason for that, if we were to use the definition from up above, if we said derivative with respect to x of e to the x power, then by definition, we would start by saying take the natural log of the base. Well, the base here is e. And then we would multiply by the exponential function itself, which would end up being just e to the x. And then we would multiply by the derivative of the exponent. Well, the exponent here is just x, so the derivative of x is just 1. Then we remember from algebra, the base on a natural log is e, and anytime we have a natural log whose base value here matches the value that we're taking the log of, then that's just equal to 1. So that simplifies to 1. This is e to the x. Obviously that times 1 is not going to make a difference. So simplifying this derivative down, you get e to the x. It's one that's, I'm going to say, very simple to find, and because it is, we usually just remember it. All right, so on here, let's find the derivatives of each of the following. Notice first that this is definitely an exponential function. So one of the things that you're going to want to do on a test is identify what it is that you're taking the derivative of. Is what you're taking the derivative of a product or a quotient? Is it an exponential? So on this particular problem, we would identify, hey, it's an exponential function. So I'm going to be using this rule that we have up above. And that's really the rule that I would remember for all exponential functions. All right, so on this particular one, notice that my exponent here, this piece would be the u talked about in the formula up above. Notice that it's not just x, so it's going to be important that on the end of this, I have the derivative of that power tacked on. All right, so let's do the three-step process here to take the derivative. So we're going to say y prime equals, your first step is to take the natural log of the base. Well, the base on this particular function is e. So we're going to start it with natural log of e. Then we're going to multiply by the exact exponential function that they gave me to start with. So it'll be e to the negative 5x squared. Then finally, you're going to multiply by the derivative of whatever the power was. The power here is negative 5x squared, so the derivative of that power would end up being negative 10x, using the power rule there, and then that's your derivative. From here, we want to simplify. We've learned from looking at the, I'm going to say derivative up here of e to the x, natural log of e, anytime you see that, that's just equal to 1. And then probably what we'll do is we'll slide this negative 10x to the front, and then we'll probably put the e to the negative 5x squared at the back. That's just a conventional way that we normally write these type of answers. So on here, 1 times negative 10, that's just going to be negative 10x e to the negative 5x squared. So if you have just an exponential function, the actual derivative of an exponential function, remember it's 3 steps, and then it's your job from there to simplify your result. All right, let's look at the next one down. On this one, we notice it's definitely an exponential function. because we have a constant base of 2, and then we notice that our variable occurs up in the exponent part. So derivative here, let's say y prime equals natural log of the base. So this would be natural log, the base here is 2. So natural log of 2, and then multiplied the exponential itself. So that'll be 2, and then to the 4x minus 1, and then multiply by the derivative of the power. We notice the power is 4x minus 1. Derivative of 4x minus 1 is just 4. Now, unlike the last one, because we were taking the natural log of e on the last one, we were able to simplify it to just 1. On this one, natural log of 2 is going to be some sort of decimal answer, and we're not going to want to simplify that. So we're going to leave that in exact form. What we probably will do is take this 4 and just slide it to the front of that natural log. Do be careful, don't multiply this 4 by the 2 in the base. That base has exponents applied to it, so you could not multiply those two bases together right now. So the 4 I'm going to slide to the front, and then I'm going to write natural log of the 2, and then multiplied by 2 to the 4x minus 1. And on that one, that would be your final answer. That's as reduced a form as you can get that answer. All right, this particular problem, be careful, don't be fooled by what it is. So looking at it originally, you might say, hey, it looks like a product, but it's really not because it's a constant multiple of an exponential. So be careful, that 5 in the front is just a constant. The actual base on this exponential function is 7. We know it's exponential since the base is a constant, and then we see that the variable has the exponent in it. Now, we do want to rewrite this, though. We're going to rewrite it as 5. And I'm going to separate that 5 out. Remember, we can do that with constants. And then this will be 7 raised to the x minus 2 to the 1/2 power. So remember here, anytime we see a root, we rewrite a root as a fractional power. Now, once that's been done, let's go ahead and take the derivative. So y prime equals the 5. I'm not going to involve in my derivative right now. And then I'm looking at the derivative of the inside piece. It's exponential, so we'll say natural log of the base, which would be natural log of 7. We would say the exponential itself, so 7x minus 2 to the 1/2 power, and then multiplied by the derivative of my power. My power was this function. So there, when I multiply by the derivative of the power, I'm going to end up having to use I'm going to say power rule, followed by a chain rule. So the 1/2 power would come to the front. The x minus 2 would stay as it is. The 1/2 power is going to reduce by 1, which is going to make it a negative 1/2 power. And then, because this is not just a singular type function, you have to take its derivative. Its derivative is 1. So don't forget your chain rule within some of these other problems. Right now, it's a matter of simplifying this down. And I know right now it looks a little bit ugly. Okay, the first thing I'm going to do is I'm going to say kind of just rearrange. You'll see we have this 1/2 kind of stuck in the middle. We have the 5 that's on the outside. Why don't we just write that as a 5/2? So we have 5/2 and then natural log of 7. And then now that we've actually taken the derivative, there's no reason for me to write it as a 1/2 power anymore. So when I come upstairs to that x minus 2 to the 1/2, just rewrite it now as a root again. Okay, that's prettier. And then coming over here, we notice that we have this x minus 2 all raised to the negative 1/2. Well, that's going to need to be down in the denominator. So there, the x minus 2 would be to the 1/2 in the denominator. And instead of writing it to the 1/2, I'll just write it now as a root. Okay, and I'll tell you, in all actuality, on this particular problem, we see the 5/2 that are sitting out in the front. Generally, that 5/2 is going to be written as the 5 that's going to go in the numerator, and then the 2 on the bottom is going to go down here with the root. So I'll make that quick adjustment. That will be the way that you see these particular problems written. So it's like they're saying, hey, the 5 was in the numerator to start with, I'm going to leave it there, and then the 2 from that 1/2 was in the denominator. Only thing that we didn't talk about is the 1. Obviously there at the end, multiplying by 1 is not going to change anything. So this particular one is done. It's a terrible, ugly looking answer. But everything's, I'm going to say, as simplified as you possibly could make it in this situation. All right, now D is something that you want to be very careful about. This one is a product. Now, what I'm going to do is I'm going to separate out that 5 that's sitting in the front, since that's just a constant. But on the inside, I'm going to have the product of x to the 4th multiplied by e raised to the x third, to the third. So on this one, we have to identify this as we're going to have to use a product rule to start the problem off. So on there, using product rule, remember there, we say keep the first. Now this 5 we have in the front, I'm going to separate it out. I'm not going to involve it in the product. All right, keeping the first, I would keep the x to the 4th. And then you do derivative of the second. Well, the second piece is an exponential. So within the product rule, I'm having to use the exponential rule. So there, the derivative of e raised to the x to the third, you're going to say it's natural log of the base, so natural log of e, the exponential function itself, so e x to the third, and then multiplied by the derivative of the exponent that's on the exponential. So the exponent on the exponential is x to the third. The derivative of that is 3x squared. Then product rule says you're going to add, keep the second function, e x to the third, and then multiply by the derivative of the first. The first is the x to the 4th. So the derivative of that will be 4x to the third. All right, I mean, make sure that you're okay here as far as this, I'm going to say, result is concerned. Remember, on product rule, what we had usually done is done a u times a v. So our u would be x to the 4th. Our v would be the ex to the third. So what we essentially did here is we said, hey, this is going to be u. All of this piece right here is going to be the v prime part, and then plus, and actually let me scooch that over because I got that a little bit in the wrong place. So all of this was the derivative of v, and then plus v, so we're keeping that second one, and then times, this would have been the derivative of the first. All right, now it's a question of simplifying this down. So what I'm going to do first is I'm going to say simplify any kind of logs I can. So we notice first we have this natural log of e. That would just go away and become a 1. Okay, then we're going to combine anything that we can. The 5 I'm going to leave out in the front for right now. All right, notice here I have a 3x squared and an x to the 4th. We can multiply that together, and when we multiply it, we add the exponents on the x's. So it would be 3x to the 6th. The natural log of e is just 1, and so all we're left with there is that ex to the third. So that just cleans up that first group of values more. On the second piece, I generally write the constant and the x part before the e to the x. So I'm just going to reorder those. So this will be 4x to the third, ex to the third. Now, the last thing that I want to consider is making sure that everything is completely factored. Notice here that we definitely have some common factors. We have a couple of x's that are common. The rule is there, if there's x's in common, you're going to pull out the least power that you have. So I would be able to pull out an x to the third. Also notice that we have this common factor of ex to the third. So we can pull that out as well. So out here with this 5, we would have a 5x to the third, ex to the third. And then left over, notice the 3 and the 4 didn't share anything, so we'll have that 3. And then as far as x's are concerned, we had 6, we pulled away 3, so that leaves us with x to the third there. We pulled this ex to the third out completely, so that's gone. And then for the second piece, we're going to have a 4. And then notice we pulled out the other 2 things completely. So that should be our final answer. On this one, you don't have to use brackets. If you want to use parentheses instead, then that would be totally fine. All right, next one down, also very important. This particular problem we notice is a quotient of a couple of things. So we're going to end up having to use the quotient rule first. And like I said, the most important thing on your exam is identifying what is it that I have to start with, and then maybe what rules will I have to use within that rule. So like here, I would have to use the quotient rule as my big overlying rule, but then within it, we see this e to the x term, which means we're going to have to use a exponential rule as well. So on here, we'll say y prime. Remember for your quotient rule, so like here, if this is u and this is v, in general, you start with v, you multiply by the derivative of u, and then minus u times the derivative of v all over v squared. So that's the idea on this one. All right, so v is 3x minus 4. Be really, really careful here. What's the derivative of e to the x? The derivative of e to the x is always itself. You have that singular power of x up there. And so on this one, when I write down e to the x right here, I'm taking its derivative. I realize it looks the same as it always has looked, but there I'm technically taking a derivative. Minus u is e to the x, and then derivative of v would end up being 3, and then all over the bottom squared. So 3x minus 4 all squared. All right, here's what I'm going to do from here. I'm going to go ahead and distribute this e to the x through to those two terms. So I would end up with a 3x e to the x, and then a minus 4 e to the x. And then over here, I'm going to reorder that a little bit, and I'm going to say it's minus 3 e to the x. And then all of that is over 3x minus 4 all squared. All right, now there's two ways that you can do this next piece. You can either factor it right away, or you can actually combine like terms. There's a negative 4 e to the x and a negative 3 e to the x that are actually common. So you could actually put those together. I'm going to go ahead and factor it. It just makes it a little bit easier to see. So in the top, we notice we have a 3 and a 4 and a 3. That didn't share anything, but they all have an e to the x in common. So we're going to pull out the e to the x term, and then that's going to leave us with a 3x, and then a minus 4, and a minus 3, and then all of that is still over 3x minus 4 squared. And then I'm going to combine the negative 4 and the negative 3. So the final answer for this particular one is going to end up being e to the x, and then 3x minus 7, and then all of that is over 3x minus 4 all squared. And notice here, nothing cancels after you've done your factorization, but you do want to make sure that you try to factor completely. All right, G, also a special problem. This particular problem, notice that we have a group of inside, I'm going to say pieces, that's all raised to a power. That's going to mean that I'm going to want to use a chain rule to start this. And basically, you're using a power rule, but then following it with the chain. So on here, y prime equals power rule with the 3. The 3 is going to come to the front. You're going to keep the inside function just the same way it is for the moment. You're going to reduce the power of 3 that you originally had by 1. That's going to make it 2. So we've used the power rule on the whole group of stuff that was raised to a power. Then you multiply on the derivative of the inside piece. So the derivative of the inside piece, derivative of 4x is 4. And then when we get to the derivative of e to the negative x squared, we're having to say there, use our rules. So for the exponential, it's natural log of your base multiplied by the exponential itself, multiplied by the derivative of its power. So it'd be multiplied by negative 2x. So that's the chain rule, I'm going to say on top of, and I'm going to say and including the exponential rule. All right, from here, we want to try to simplify as much as possible. The first piece I'm going to say is pretty simple, so we're just going to leave it alone for right now. All right, and then the thing we need to work on is this inside piece. That right there, natural log of e, that'll be 1. Notice here we have a times negative 2x. I think I'm going to slide that to the front of that term. So 4 I'm going to leave alone. So we'll have 4 minus 2xe raised to the negative x squared. Now, the only thing I really need to do at this particular point is make sure that this is factored completely. Notice here that these two terms share a factor of 2. So I'm going to pull out a factor of 2. That factor of 2 that I'm pulling out, I'm going to multiply by the 3 that's already in front. So 3 times 2 would end up being 6. And then I have 4x plus e to the negative x squared. And then I pulled out a factor of 2, so that's going to make that a 2. That'll make that an understood negative 1. And then I'll have the x e to the negative x squared. Now, generally, what we do is when we have negative exponents, we rewrite them as positive exponents. If you'd like to do that, you can. I'll also explain to you here, though, I don't know what the value of x is. And so sometimes when you have a variable that's up in a power, you can't truly tell if your exponent is going to be positive or negative. But you could definitely give this to me for a final answer. That would be okay. Or you could also give this to me. And either one of those two forms would be fine. All right. As our last example here, let's look at an application. It says the population of Australia in millions can be described by the growth function, a of t equals 10e raised to the 0.009t for t years after 2005. Okay, now on here, you kind of have to be careful. When it says t years after 2005, that basically means that in 2005, my t value would be 0. So that's the initial year. It says, what is the rate of change? And you need to think of rate of change as being derivative of Australia's population in the year 2014. The first thing we need to do here is convert 2014 to a t value. So the way we do that is we say it's t equals, you take that year, 2014, and you subtract off the original year. So the original year was the year 2005. And so here we would basically say, hey, it's been 9 years since 2005. So if we're looking at 2014, our t value is 9. So on here, we're going to do 2 steps. We're first going to find the derivative of the function that they gave us. Notice the function that they gave us was an exponential type function. So to find its derivative, we're expecting to use an exponential rule. So let's do a prime of t. Now notice up here that the 10 is just a constant. So I'm going to separate that out and not involve it in the derivative. So 10. And then on the inside, the derivative of e raised to the 0.009t, I would do natural log of the base, which is natural log of e. And then I would say then multiply by the exponential itself, so e raised to the 0.009t. And then I would say multiply now by the derivative of the power. The power, its derivative, you notice, would just be the constant out in the front. So that would be 0.009 for its derivative. Be careful here about your justification. We notice that this piece is up in the power. The 0.009 here is down at the same level as the base. All right, and I guess to be consistent, let me come back here at the back and let me write that not as a parentheses, but as a bracket. And that's just going to make it look a little bit better there. All right, now we're going to simplify. Natural log of e we know reduces just to 1. Okay, and then also from here, what I can do is say we have the 0.009 multiplied by the 10. Well, what that's going to do is move your decimal point over one place. So there we can do 0.09. And then we're going to have e raised to the 0.009t. So that's about as simple as we can make that derivative. Now, as your second step, we're going to go and plug in, I'm going to say the 9 that they indicated there for the year amount. So they said they wanted to know what the population was specifically in 2014. So our first step was to take the derivative, and our second step is to evaluate that derivative at the 9. And at this particular point, I would expect you just to plug this in on your calculator. Your calculators are going to have an E button on it. I'll show you when you plug this in your calculator, what you're probably going to need to do as far as the exponent is concerned. On your calculators, once you find your E button, make sure that you're raising to a power and also make sure that you're putting the entire power in parentheses. If not, what is going to happen is when you multiply by that 9 is going to be down in the base instead of up in the exponent. So just be really careful here on your calculators. Okay, if you need any help with your calculators, you can definitely let me know. All right, on this particular one, doing that on your calculator, you're going to get 0.09759333807. Now this particular problem, be a little bit careful because it said the population is in millions. I'm going to say that number as a population definitely does not make sense. But we said, hey, it's in millions, so at this particular point, we need to come multiply this number by 1,000,000. All right, and doing that, we're going to end up with something that makes much more sense. So this is going to be 97593, and that's going to be slightly rounded. We want to round there to the nearest whole number, and then this will be people per year. All right, let me know if you have any kind of questions.